I talk here about our work on using eye gaze for assistive manipulation. Robots are used to help people perform many tasks, from remote surgery to space exploration. One exciting use is for assistive robots, or robot arms that mount on wheelchairs and help people to perform activities of daily living. However, teleoperating a robot to perform a complex task is very difficult for people. Controlling a 6-degree of freedom manipulator arm with a low-dimensional input device is non-intuitive, and handling contact in the workspace makes the problem even harder. To make the problem easier, we can add autonomous behavior. This system infers what the user is trying to do with the robot, then provides a signal to assist in the task. People's natural eye gaze is a powerful signal for understanding their intentions. People's eye gaze behavior while they manipulate objects with their hands has been a topic of research in psychology for decades. While using their hands to perform tasks, people look almost exclusively at the objects they are trying to interact with or avoid, and rarely look at objects that are not relevant to the task. In this work, we show how to use mental state insights from gaze behavior to improve robot assistance. First, we collect data on people's eye gaze behavior while they teleoperate a robot. Next, we develop a pipeline for automatically processing raw eye gaze into a contextual representation. Finally, we discuss two types of assistance that the eye gaze signal enables. To understand what people look at while teleoperating a robot, we performed a study in which participants were asked to spear a marshmallow using a fork held by the robot. In this study, we found that, like in by hand manipulation, people look at task-relevant objects, particularly the morsel they are trying to spear. However, people also spend a lot of time looking at the end effector of the robot. In addition, we found that when something goes wrong in the task, for example, the robot goes into a bad kinematic configuration, people look at the source of the problem. These insights enable us to design gaze-based assistance strategies. Next, we process the raw gaze data into a lower dimensional and context-rich representation. The raw eye gaze data is first clustered into individual fixations. Each fixation is labeled with an object in the scene. This sequence of labeled fixations enables machine learning approaches for intent recognition. Finally, we introduce two strategies for incorporating gaze into assistance. First, we discuss inferring people's goal from gaze. Earlier work infers people's goals from their controller input. We note that gaze provides a complementary signal for inferring people's goals. The joystick input provides immediate direction towards the next step, while gaze gives absolute information about the final goal. Second, we introduce a new type of assistance, responsive obstacle avoidance. Here, we hypothesize that people will look differently at obstacles depending on how concerned they are about them. It will be reflected in their eye gaze behavior. Therefore, we can design an assistance strategy that measures their sensitivity to a particular object and adapts the robot's trajectory accordingly to give sensitive obstacles a wide berth and more efficiently move around safer obstacles. In this project, we use eye gaze for intention inference to broaden the possibilities for assistive teleoperation and more generally human-robot collaboration. Thank you.